Did you know that Airbnb has over 4.5 million property listings worldwide, hosting millions of travelers every year? It's one of the biggest platforms connecting people who need a place to stay, with hosts offering unique homes, apartments, or vacation rentals. But how does Airbnb make sure that both guests and hosts are happy with their experience? That's where machine learning comes in. Airbnb operates in a two-sided marketplace. On one side, we have the guests, people who are looking for accommodation. On the other side, are the hosts, people offering their places to stay. When a guest requests to book a property, the host has the option to accept or reject the request. But not all hosts are the same. Some hosts aim to maximize their occupancy by accepting bookings that fill short gaps between other reservations. Others prefer to host occasionally and may not be concerned with keeping their calendar full. Preferences can also vary between big cities and smaller markets. So, how does Airbnb handle these different preferences while ensuring a smooth booking process? The answer lies in machine learning, which has helped Airbnb increase booking conversions by 5%. Today, we'll dive into how Airbnb uses AI to match guests and hosts more effectively. Let's break it down and see how this works in real time. Stay tuned as we explore the magic behind Airbnb's booking success. Understanding host acceptance decisions. Now, let's talk about one of the most important factors in Airbnb's booking process: host acceptance decisions. When a guest sends a request to book a property, hosts have the option to accept or reject the request. But what exactly influences their decision? A common reason hosts may reject a booking is due to the gaps it leaves in their calendar. For example, let's say there's a request to book a stay from April 5th to April 10th. If accepted, it could leave a gap in the days before or after this booking, like a check-in gap from April 5th to 7, or a checkout gap after April 10th. Hosts who want to maximize their occupancy will try to avoid these gaps because they can be hard to fill with new bookings. Interestingly, not all hosts prioritize high occupancy. Some prefer to host occasionally, while others may not mind having gaps between bookings. It was discovered that hosts in larger markets, like big cities, are much more focused on maximizing occupancy. In fact, they are 6% more likely to accept a booking that leaves no gap at all. On the other hand, hosts in smaller markets prefer to have a few days between bookings, showing that preferences vary across different locations. Another factor that affects host decisions is the timing of the booking. On average, most Airbnb hosts prefer bookings made at least a week in advance. But not all hosts share this preference. Some actually prefer last-minute bookings, while others favor far in advance stays. These differences show that hosts' preferences are not uniform. They can vary widely depending on their individual needs. All these insights led Airbnb to a powerful conclusion. By using machine learning, it is possible to promote search results that match not only the preferences of the guests but also the preferences of the hosts. In this way, hosts who are more likely to accept a booking can be promoted in search results. This creates better matches for both guests and hosts, leading to more successful bookings, happier experiences, and a significant increase in booking conversions. How host preferences were modeled. Once the patterns in host preferences were identified, the next step was to model these preferences using machine learning. A team of data scientists and software engineers worked together to develop a personalized search signal. This signal was designed to connect past host decisions, whether they accepted or declined bookings, with various characteristics of the trip, such as the check-in date, checkout date, and the number of guests. The goal was to improve Airbnb's ranking model by incorporating host preferences alongside guest preferences. By combining both sides of the platform, hosts and guests, it was hoped that the system could generate better matches between the two. At first, this problem seemed to fit into a technique known as collaborative filtering. Collaborative filtering is used in platforms like movie and music streaming services, where user preferences for items like movies or songs are predicted based on past ratings. However, Airbnb's case was a bit more complex. Unlike movies or songs, no two trips are exactly the same. For instance, behind every booking request is a unique guest with different needs. This makes it hard to predict a host's acceptance decision based solely on past data. Hosts could accept or reject similar requests based on various personal factors. Also, a host may receive multiple requests for the same trip but from different guests, leading to different acceptance decisions. To address these challenges, the team simplified the problem. Instead of analyzing all the factors at once, like trip length, guest party size, or the size of the calendar gap, each characteristic was looked at separately. This allowed the data to be clearer and reduced conflicting labels for the same trip. For example, instead of trying to understand all the host preferences at once, they focused on each trip feature individually, such as how long the trip was or how far in advance the request was made. This helped to resolve some of the noise and allowed for a clearer understanding of what hosts preferred. Still, the data wasn't perfect. In fact, for around 26% of hosts, there wasn't enough data to understand their preferences because they hadn't received enough relevant booking requests. To fill in these gaps, a method called imputation was used. The team applied a weight function to smooth out the data. This function combined the median preferences of hosts in the same region with the individual host's data. For instance, if a host didn't have enough data points, the system used the average preferences of similar hosts in the area. As more data was available, the system shifted to the host's specific preferences. Using this new structure of preferences, the team developed predictions for host acceptance rates using a logistic regression model. Logistic regression helps to predict the probability of certain outcomes based on several factors, in this case, the probability of a host accepting a booking request. Each trip characteristic, such as the check-in date or the number of guests, was given a weight. The model then combined all these factors into a single prediction for whether the host would accept or reject a booking request. The model was then tested on segments of hosts using a user-generated function, UDF, in Python. This function analyzed accommodation requests, host responses, and other data points. It either built preferences for trip characteristics or trained the logistic regression model to predict outcomes. The model's performance was evaluated using a metric called mean squared error, MSE, which measures how accurate the predictions were. In offline testing, the new model showed a 10% reduction in MSE compared to the previous version. This was an encouraging result, but the final test would come when the model was tested live on Airbnb's platform. Experimenting with the model, now, let's move on to an interesting part of how Airbnb tested their model using experiments. Once the model was built, an experiment was launched to see how it performed when put to the test. In this case, the model was designed to predict the probability of a host accepting a booking request. This predicted probability was then added as an important factor in Airbnb's search ranking system. Here's how it worked. When a guest in the treatment group searched for a place to stay, our model would calculate how likely each host was to accept that guest's request. The listings with higher chances of acceptance were ranked higher, which increased the chance of a successful match. Measuring the success of the experiment, to see if the model actually improved results, several metrics were used to measure success. The most important one was booking conversion, how likely it was that a guest's request would turn into a booking. As a result of this experiment, a 3.75% increase in booking conversions was observed. This means that more guests successfully found and booked places to stay. It wasn't just a small improvement, there was a noticeable rise in successful matches between guests and hosts. Further optimization and results, but it didn't stop there. After the initial experiment, some optimizations were made to the model. These adjustments added another 1% improvement in conversions. This brought the total increase in booking conversions to around 5%. Once these optimizations were complete, the new model was rolled out to all users. This marked a big milestone in Airbnb's journey of improving how they matched guests and hosts, making it a key contributor to the platform's success.